The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Wireless Fantasy by Vladimir Ussachevsky. It's one of the first pieces of computer-generated music. It was done at Columbia University in 1960. It was commissioned by a group of fans of Lee DeForest, and it was in honor of DeForest's contribution to wireless broadcast. So and one of the first broadcasts DeForest ever sent over the radio was the piece that you're hearing. It's Parsifal. It's from the Wagner opera. And so what Ussachevsky has done in the piece is to process it to make it sound really distant, as though it's coming over a shortwave radio. And then he's got Morse code. And there's various Morse code messages going through the piece. Wireless Fantasy from 1960. Done longhand, by the way. It was really done with Morse code and a mainframe computer and giant reel-to-reel decks. Nothing like what you have on your desktop today. Okay, so announcements. Tomorrow will be the exceptional Thursday test, quiz 5 based on homework 5. Last day we talked about the band theory of solids, and in the band theory we were able to distinguish metals from insulators from semiconductors, and you can see up here the metal has a very, very tiny energy gap between the top of the filled orbitals and the bottom of the unfilled orbitals, so it's effortless to move the electron up into this zone and give it mobility. In an insulator, there's a substantial energy required to move from the filled orbitals to the unfilled orbitals, which we neatly refer to as the valence band and conduction band. And arbitrarily, we've chosen 3 electron volts. Typically, the insulators are up 4, 5, 6, and so on electron volts. And then there's this class of materials, semiconductors, for which the band gap is on the order of 3 electron volts. And why is 3 such a magic number? Because 3 electron volts is the threshold of visible light. So materials that have energy gaps below 3 electron volts will respond to visible light. And we're going to talk about such matters presently. And just the last point to make is that the valence band is constructed of the smearing of, or the splitting of orbitals that are associated with bonding. So valence band is valence electrons in bonding orbitals, and the conduction band was generated from anti-bonding orbitals. And then we looked at photoexcitation. If we have incident photons that have enough energy to break the bonds, electrons will be promoted up into the conduction band, and it's a momentary transit, and they will subsequently cascade back down. And when they do so, a photon will be re-emitted. When the electron cascades down, photon will be emitted, and the emission will be pegged at the band gap energy. So if we go into Hc over lambda, lambda becomes a critical value that's associated with this particular material. And so we can plot percent absorption of what? Percent absorption of incident light as a function of the energy of that incident light. So high wavelength, low energy light will pass through. It'll be transmitted, and the material will appear transparent. High energy, that is to say low wavelength incident radiation, will have enough energy to promote electrons, and so therefore those incident photons will be absorbed. The excess energy will be dissipated up here as heat, and then we'll get re-emission of photons. And so over here the material is an absorber. And so we have a sharp jump here at a critical wavelength, which we term the absorption edge. And then towards the end of the lecture, we talked about another type of excitation. This was photoexcitation. We're going to talk about thermal excitation, where the thermal energy in the environment is enough to cause the breaking of the bonds and the promotion of the electron from the valence band to the conduction band. But in this case, we discovered that pair of carriers was generated, not a single carrier. In the case of photoexcitation, the electron moves up, falls back down. Here we have pair excitation. So what happens is this electron is permanently, sustainably sitting up in the valence band, leaving in its place a broken bond, which consists of a single electron and a missing electron, which is termed a hole. It is 0 in a land of -1, so it appears to be +1. And this is -1 in a land of 0, so it appears to be -1. So you see charge conservation. The population of electrons in the conduction band due to thermal excitation is equal to the population of holes in the valence band. And electrical engineers like to just refer to the charge, the nature of the charge, regardless of the carrier, whether it's a positive ion or a positive hole. As far as they're concerned, it's a positive. So the electrical engineers write this relationship, N equals P. The number of negative charges in the conduction band equals the number of positive charges in the valence band. And then I left you with this mystery at the end of the lecture. I said, well, we observe thermal excitation in semiconductors, but the thermal energy is roughly related to the product of the Boltzmann constant times the temperature. And in electron volts, this amounts to about 1/40th of an electron volt at room temperature. But the band gap energy in semiconductors is on the order of several electron volts. In the case of silicon, it's 1.1 electron volts. So how can we justify any kind of thermal excitation given that the thermal energy is so much lower than that of the band gap energy? Well, I have good news. The answer is that the energy in this room is distributed amongst all of the entities in the room. So that if you look at the gas, for example, let's go back to the 1850s and peer into the mind of James Clerk Maxwell, who also gave us Maxwell's equations. He was a polymath like so many of the other people that we've been talking about in 3091. He didn't just focus on electromagnetism. He was a Renaissance scholar. And so one of his areas of interest was physical chemistry, and he studied gases. And he reasoned that the gases have a distribution of velocities. All of the gas molecules in this room are not behaving as though they are at room temperature. A substantial number are, and that's how we establish temperature. But what Maxwell reasoned was that some gas molecules are moving around as though the temperature of the room is 500 Kelvin. And some are moving around as though it's only 100 Kelvin. But a large number of them are moving around as though it's roughly 300 Kelvin. So he gave us a mathematical formulation of the distribution of energies. And then, about 25 years later, Boltzmann came along and said, you know, I'm going to generalize this idea. I'm going to generalize the idea. Forget about just gas molecules and velocity. Let's talk about all molecules. And say the reason the gas molecules are moving mainly at 300 Kelvin and that some are moving at 500 Kelvin is, and this was a big leap for Boltzmann, he said, I'm going to propose that temperature is distributed as well. That the reason some gas molecules are moving as though they have the velocity of 500 Kelvin is that I'm going to propose that they have the energy of 500 Kelvin. Well, what is local energy? That's temperature. So Maxwell and Boltzmann, we put the two of them together and we come up with the notion of a distribution of temperature, a distribution of energy. And this is what that distribution looks like. What we do is we plot the number of particles in a particular ensemble that have a particular energy as a function of energy. And then we'll normalize it over the total number of particles in the system. And, you know, before I do that, why don't I just do an analogy? I'll do, you know, we had the test a few weeks ago. Let's do a distribution of grades, and then we'll relate it. Okay? So, for example, what I could do is I could plot grade on this axis, and I could put the number of people who have a particular grade, and then normalize it, divide it by the total number of students in the class. And if it's a big class, as this one is, and we have some kind of reasonable test, we expect to see this kind of a distribution, a bell-shaped curve, a Gaussian distribution. All right? And what does this tell? It tells us that some people had greater than the average value, some people had less than the average value, but the average value is given here. It's a symmetric distribution. And so we can call this the average. This is the average grade, G with a bar over it. And you get the inflection point here. This is where the second derivative shifts from positive to negative. That's how you get the standard deviation. This is G bar plus standard deviation. This is G bar minus standard deviation. You can have a lot of fun with this. And the area under this line, if I use normalized values, the area under this line must equal 1, right? Area equals 1 when I normalize from 0 to infinity. So let's do the same thing here, only this is Gaussian. This is Gaussian. But that's not the way molecules are distributed or energies are distributed in an ensemble. It's asymmetrical. It looks a little bit like this. It's got a sharp rise and a long asymptotic tail. And so the average is not at the maximum in this case. This is Maxwell-Boltzmann. This is Maxwell-Boltzmann. We have a distribution of energies, and the average, the energy average, E with a macron over it, is somewhere a little bit to the right of the maximum. And so what I'm doing is I'm taking the energy of a particle, the number of particles that are given energy divided by the total number of particles, so also the area under this curve must equal 1. So this is the value at some T1. And what I want to do is I want to focus down here. Suppose up here this is 1.1 eV. 1.1 eV. Well, the average value is here, and I said that this was 1/40th of an electron volt. That's not the problem. The problem is not that the average is a 1/40th of an electron volt. The good news is that there is some tiny fraction of the distribution that has energy above 1.1 eV. So if I knew what that fraction was, then I could guess how much I could expect in the way of promotion here. You can see it's non-zero. It's not a sharp cutoff. There's a tiny value out here. And the nature of this curve is that the amount of the fraction of the distribution out here, if I want to integrate, say, from 1.1 eV out to infinity, that's the area under this line. What am I integrating? I'm integrating the fraction times dE. This equals e to the minus energy gap divided by K Boltzmann temperature, this exponential. That's what gives us the fraction underneath this line. Now let's see what happens when temperature rises. When temperature rises, this line shifts to the right. This line shifts to the right. And as you would expect, the average shifts to the right as well. So this now is E average at T2. And, okay, let's say I raise the temperature. Let's look at silicon. So let's say T1 is equal to room temperature 300 Kelvin, and T2 will be the melting point of silicon. T2 is the melting point of silicon, not to make liquid silicon. It's solid silicon at the melting point. So it'd be like ice at 0 degrees C. Melting point of silicon is 1414 degrees C. So add 273 to it and get about 1700. It's about 1700 Kelvin. So what's the ratio? T2 to T1 is on the order of about 6. So this thing shifts by a factor of 6. Let's look at what happens in here. Let's look at what happens in here. So I'm going to use I'm going to blow this up. We'll blow this up. So what we're really looking at is what's the difference between the area here at room temperature, and then what we're going to do is not to scale. We're going to look at the area under the green curve. And when we use this relationship, e to the minus energy gap energy over kT, band gap energy over kT, we find that the fraction at T2 divided by the fraction at T1 comes out to be 10 to the 15th. So changing temperature changes the excitation population through the shift in the high end of the curve. And it's only through that that we end up seeing decent levels of population in the conduction band. But so actually the number at room temperature is vanishingly small. At room temperature, the fraction in the conduction band is about 10 to the minus 19. There's so few of them you can give each of them a name. So there's almost no conduction. Silicon at room temperature is an insulator. So if we want to get some conductivity, are we going to heat our computers up to such a high temperature? I don't think so. So we need some other way of populating the conduction band, and we're going to do one other mode of promotion. We've looked at photoexcitation, thermal excitation, and the third mode is chemoexcitation. Chemoexcitation. What we're going to do is we're going to get carrier injection by introducing impurities. by introducing impurities. And I know you're sitting there thinking, he's crazy. We just spent all of this time and money making silicon 6/9 purity, and now we're going to start throwing impurities into it. Well, there's two kinds of impurities in this world. Two kinds of impurities. There are good impurities and bad impurities. All right? The good impurities are called dopants. These are the ones that are there desirably. Okay, so dopants are good guys. And then there are other ones that are called contaminants. And these are undesirable impurities. So we don't want contaminants. So we're going to look at dopants. And this is a really important lesson right now that I'm teaching you. What I'm showing you for the first time in 3091 is how we can use chemistry to alter the performance of a material. I'm going to take plain high purity silicon, which is an insulator at room temperature, and by operating on its chemical composition, give it properties that it cannot possess otherwise. So this is a paradigm. This is a paradigm for solid state chemistry. You want something that's got a higher yield strength, we'll change its composition. You want something that's got a higher conductivity, we'll change its composition. That's different. That's different. Okay, so this is an engineered material. This will be engineered material. And how is it engineered? Engineered material, what we're getting is via chemical change. Via chemical change, purposeful chemical change. So we're getting, if you like, tailored composition. Tailored composition. Tailored composition to give targeted properties. And this is what underlies material science. If you don't see what you like, make it. And how do you make it? By understanding the relationship between electronic structure, bonding, and ultimately properties. So here's what the gambit is. Now I'm going to talk only about elemental semiconductors. So in the case of silicon and germanium, I'm just going to restrict today to silicon and germanium. That's not such a bad restriction since we're in the silicon age. All of your micro devices contain silicon. So this is pretty good. So here's the gambit. You introduce aliovalent impurities. Introduce aliovalent impurities. What do I mean aliovalent? Alio is the same as the Latin word for alias, other. So we are going to introduce impurities that have a different valence from silicon and germanium. Silicon and germanium are group 4, or group 14 if you want to use UPAC notation. So what I'm going to do is introduce something else. I'll give you an example. So, and the purpose of introducing aliovalent impurities is to cause electron donation or electron consumption. And how's that going to work? Well, you'll see it best in action. So here's a simple example. Let's put phosphorus in silicon. Phosphorus, as you know, is group 15 or group 5. So it's got 5 valence electrons. And let's first look at the Cartesian world. So here's silicon. It's sp3 hybridized. And it forms a diamond-like solid, right? Diamond-like solid. So it's crystalline, it's regular arrays, silicons at all of the corners of the tetrahedra, and on it goes. I'll give about 3 of these. Okay? So now what happens if I introduce phosphorus? If I introduce phosphorus, the phosphorus actually goes in and substitutes for silicon. So the phosphorus substitutes. It doesn't go and sit in some void space. It actually substitutes for silicon. Now, if it's going to substitute for silicon, it has to form bonds. Agreed? You can't just sit there. There's no passive observer here. If you want to play, you got a bond. So phosphorus comes in with 5 valence electrons. So it goes 1, 2, 3, 4. There's 4 of its valence electrons are bonding to the 4 adjacent silicons. What happens to the 5th valence electron of phosphorus? There's no empty orbital in which that 5th electron can sit. So that 5th electron is sitting here, kind of tapping its foot, wondering what it's going to do. Well, let's go over to the energy level diagram. Here's the energy level diagram. This is silicon, elemental silicon. Downstairs is valence band, upstairs is conduction band. When we put the phosphorus into the silicon, where in energy space, where's the only place that fifth electron can go? There's no room at the end down here. All of the valence orbitals are filled. So the only place it can go is up here in the conduction band. So here's the electron that came from phosphorus. It was donated from phosphorus. We call phosphorus a donor. Okay? This is a donor electron. And can you see that every time I throw a phosphorus in, I'm going to get an extra electron in the conduction band. So if I want to increase the conductivity of silicon, just keep adding phosphorus. 1 for 1. Oh, but am I making holes down here? No, I'm not breaking any bonds. In fact, I'm forming bonds here. There's an extra electron. Everything's fine. So now I've got a lever. I can dial in how much conductivity I want. You want to raise the conductivity to a certain value? I can tell you how much phosphorus to add to get to that level of conductivity. And this electron's not in a valence band. It's not bound, so it can move. So this goes back to Paul Drude. These electrons are free to roam because they're not bound. But I'm going to show you something. I'm going to show you something really cool. How far can that electron roam? So think about it. Phosphorus is a 5 valent. So it's got an extra proton too, right? So this phosphorus is a 5 plus and a lambda 4 plus. So the phosphorus you can think of as locally plus. And this electron that didn't go into any of the valence band orbitals, it's locally minus. Duh, an electron is locally minus. That's deep. Okay, so here I've got the phosphorus that's locally plus, and I got the electron that's locally minus. Do you know of a model that might describe the motion of an anchored positive charge with an electron that's free to roam? Do you know of a model that might talk about such things? Bohr. So let's do something really whacked. Suppose we said, we took this electron and we said, let's ask the question, if we applied the Bohr model to this pair, what will we come up with? I mean, it's going to give us energies, it's going to give us radii, it's going to give us velocities. Do you think there might be a relationship to velocity and mobility and conductivity? And well, let's see where it goes. So let's go. So what I'm going to do is I'm going to say, remember recall in hydrogen and atomic hydrogen, recall in atomic hydrogen, the ground state energy, this is the electron at the bottom of the, is minus K, what we've been calling K, which has this full-blown formula of me to the 4th over 8 epsilon 0 squared h squared, and plug in all the numbers and you get minus 13.6 electron volts. Minus 13.6 electron volts. Now, let's think about this. We're going to have to make a few changes. Epsilon 0, that's the permittivity of vacuum. But if you're an electron, you're looking down at the phosphorus, it's not just vacuum between you and the central phosphorus. There's all this stuff. There's bonds. There's silicon nuclei. So I've got to modify this. I've got to change this. So what I'm going to do is I'm going to take epsilon 0, which is what we have for vacuum, and I'm going to replace it with epsilon. Epsilon of silicon. Epsilon of silicon. Silicon is the host crystal. So what does this capture? It captures all the bonds, all of the silicon, all of the stuff. Okay? So that's the dielectric constant. That's the dielectric constant of the host crystal. And there's one other thing. This is some esoteric physics. I'm just going to put it up here without proof. When you're in this situation, you don't use the rest mass. There is an effective mass. The effective mass, and that invokes a slight correction. The effective mass of the electron at the bottom of the conduction band. Bottom of conduction band. This is a minor correction. The main correction is getting the dielectric constant, okay? So this second one is there for completeness. Some of you are going to look back fondly at these notes and say, yeah, we got it, this was good. Otherwise, you say, hey, how do we lift out the effective mass? So can't say that now. All right, so here are the values. For silicon, the dielectric constant is 11.7, and the effective mass at the bottom of the conduction band is 1/5 of the rest mass. So I'm going to plug these values into this equation, and what this gives me is then that the ground state energy of the donor electron is minus K, as we had before, and it's going to be multiplied by 0.2 on the top, and then I'm going to have an 11.7 squared on the bottom, and that gives me minus 0.02 electron volts, 2/100ths of electron volt. This quantity has been measured. The measured value, compare with CF. CF 0.045 eV. Measured. And you might say, well, that's more than double that. And I'll say, but wait a minute. You know, we started at 13.6 and I took it down to 0.2, and you're telling me, yeah, but the real value is 0.4. I said, you don't appreciate good work. That's what. This is fantastic. This is fantastic with a simple, primitive Bohr model and 2 minor corrections to zoom into condensed matter and give this value. So where is that going to be? Where is that going to be? 0.02 south of what? It's going to be here. This is where that lies. This distance here is the 0.02 electron volt difference. You're 0.02 electron volts below the conduction band. You're not down here. This is valence. You're up top. And the electron's sitting in there because that's the ground state. So now you're saying, well, that's really great, Sadoway. Now you've got an electron sitting in an orbital. Now, how are you going to get it up to here? I got an answer for that. But first look at this. I couldn't resist this derivation. I said, what about the radius of the orbit? How far is that electron away from the phosphorus? You know, is it in tight? Is it in moving around like this? Or is it way, way out here? Doesn't that intrigue you? Sure intrigues me. So here's what I did. I said, okay, the R1, the radius of this ground state, was going to be given by the Bohr radius times the modified dielectric constant divided by the modified mass. And when you plug in the numbers, you get 30 angstroms. 30 angstroms. We say, well, I don't know what the silicon-silicon distance is. Well, what do you think it is? I mean, you know it's got to be on the order of a couple of angstroms. So if you compare that, the silicon-silicon distance is 2.35 angstroms. So this electron's way, way zooming around. So, fantastic what we've learned here. Now, let's look at this. So we've got the electrons sitting in this energy level down below, and now what happens? Well, how do I get this thing to move out? What am I going to do to make it move out? Well, what do I have? I know that the energy is 0.02, but how do I compare this energy with? Compare this with the thermal energy. E thermal is on the order of 0.025, 1/40th of an eV. So the thermal energy is so high at room temperature that it's able to promote these. And by the way, you know, if this Bohr model works for ground state, what would happen if I were to blow this up? Can you imagine that if this is the conduction band, I get all of the energy levels. I get the whole Bohr energy state here. I get ground state, n equals 2, n equals 3, all the way up. And now I have enough energy from thermal energy to take all of these electrons, because each one of these comes in because it's a separate phosphorus and they're far enough apart, they're separate states. All of these can get promoted. What do we call this action if I take a ground state electron and hydrogen and I get it right out of all of this set of energy levels? What do we call that process? We take the electron and we throw it out of the system. Ionization, and that's exactly what the electrical engineers call this process. They call the thermal excitation of the donor electrons ionization. So for all intents and purposes, because E thermal is on the order of this E of the donor electron, we can assume complete, and I'm going to use the electrical engineering term here because I think I'm still teaching at an engineering school, complete ionization of donor electrons. Oh, this is fantastic. This is fantastic. They're all ionized. So now, last day I said that the total number of electrons in the conduction band would equal the number of electrons from the host silicon, right? Host silicon due to thermal excitation. Plus, it's going to be the number of electrons from the impurity phosphorus. Okay? And we know this requires Eg on the order of about 1.1 eV, so very few of these are contributed. There's almost no promotion of electrons from the valence band to the conduction band to leave holes. This is vanishingly small at room temperature in silicon. Whereas here, because I'm going to put in quotation marks, the ionization energy is on the order of the thermal energy, we get all the electrons from here. And so in such a material, we say that the electrical properties are essentially those as from the impurity. So we send this to 0, and we say that such a material exhibits extrinsic behavior. Extrinsic behavior. Why is it extrinsic? Because the behavior of the electrical behavior of the silicon is governed by the impurities that we introduced into the silicon. Okay? Extrinsic behavior, and it is impure, or let's call it dopant. I'm going to use the word dopant and impurity interchangeably. So it's dopant dependent. And this, of course, depends on how much we put in, but the typical levels that we put in are great enough that they swamp the value that you get from thermal excitation. So in doped silicon, you neglect thermal excitation, and you calculate the carrier population in the conduction band based on how much phosphorus you put in. Every phosphorus gives you a contribution. And just to complete the definition, the undoped material, the undoped, that is to say, highly pure silicon, exhibits intrinsic behavior. In other words, it behaves as pure silicon should behave. So an intrinsic semiconductor is one that has impurity levels so low that they don't manifest themselves. An extrinsic semiconductor has impurity levels high enough that we can perceive the action of those impurity levels. So we can say in this material that N that are generated from the impurity or the dopant are greater by far than the N from the host material itself, or if you like, the number of electrons from the dopant are much greater than the number of electrons from thermal excitation. It all comes out to say then that the number of electrons that are up in the conduction band are much greater than the number of holes in the valence band, because if the impurity levels are dominating what comes out of the host, then that means if there's hardly any of the electrons that came from thermal excitation, there's hardly any holes. So now the number of electrons far exceeds the number of holes, so this material is not net neutral. We do not say that N equals P, because the number of electrons in the conduction band is far greater than the number of holes. And so we call this material, it's extrinsic, and electrical engineers refer to the type of carrier that's dominating. It's electrons, and electrons when I went to school were negative, so this is an N-type semiconductor. Extrinsic N-type. So we altered the electrical properties of silicon by introducing high level of supervalent. In other words, phosphorus, 5 is greater than 4. So supervalent dopant leads to N-type semiconduction. And now we can do it all over again. We can do it all over again. Well, what can we do? Well, repeat with, and I'm not going to drag you through it. This is something you can do at home or wherever you like to work. Repeat with subvalent impurity. Repeat with subvalent impurity or subvalent dopant. So, for example, boron. What would happen if we were to introduce boron here? So boron goes into the space, and it substitutes. But boron is group 13 or group 3. So boron only has 3 valence electrons. So it fills 1, 2, 3. And boron is electropositive. It's sitting there. It wants to form the bond. How do we handle this situation? What do we do in order to balance the fact that this is lacking 1 electron? Where is the electron inventory in this crystal? Where's the electron store? If I go shopping for electrons, where's the only place I can find them? They're here. They're in the bonds. That is to say, they're in the valence band. So what will happen is we will rip an electron out of the valence band and move it over to here. And when we do that, what happens if I take an electron out of here? What's left behind? A hole. So let's generate a hole. So every time I introduce a subvalent impurity, I call for an electron out of the valence band and I generate a hole. And where's that hole going to lie? We can go through the same analogy and we will find that the energy level of that hole is sitting just above the valence band. But the electrons are sitting in the valence band. So how do I get the electrons out of the valence band up into this level? Thermal excitation. And guess what this energy difference is? It's on the order of the thermal energy. And so I get thermal ionization of the valence electrons up into this level. This level is a place where electrons go. It accepts electrons. It is called the acceptor level. Acceptor level. Acceptor level. So now we have this configuration. Conduction band, valence band, subvalent impurity. This is not to scale, of course. This is on the order of 0.02 eV. Okay? And this is called the acceptor level. We get thermal excitation, leaving holes behind. So thermal excitation promotes the electrons up to here and leaves behind holes. So every time I put in a subvalent impurity, the result is a hole. So I can control the hole population. And the same thing will happen. If you go through this analogy, what will happen? N will no longer equal P. Instead, the number of positives is going to exceed the number of negatives. Now Ne will be much less than NH. N will be less than P. And so this material will be rendered a positive conductor. It's going to be dominantly hole conduction. So this is now a P-type semiconductor. Extrinsic P-type semiconductor. So what's the template here? Subvalent dopant. Subvalent dopant calls for electrons, generates holes, and makes a P-type semiconductor. That's amazing. So now I can take these, I can make a sandwich out of these things, you know. I can do this. I could say this is all silicon. Okay, I could dope this side with phosphorus, this side with, let's say this is phosphorus doped. The right is phosphorus doped. The left side is boron doped. So that means that the left side will be P-type. The right side will be N-type. And what do I have here? I have a P-N junction. I have a solid state rectifier. If I put an AC signal in here, I get rectification. Solid state. This is the solid state. It's fantastic. Well, you know, I've been talking about elemental semiconductors, but these are found not only in elements. Oh, this is just leftover from last day. We saw this last day. You can have compounds that are semiconductors. So far we talked about just group 4. We talked about silicon and germanium. Tin is very, very mildly semiconducting. But these are the two workhorses, and in fact, it's dominantly silicon. But now, look you can take group 3 and group 5, and you'll make covalent compounds, and they too have band gaps on this interval. So we have an entire palette here that we can paint on. So for example, let's look at this homologous series with aluminum. Aluminum antimonide, 1.52 electron volts band gap. Aluminum nitride, 6.3. Aluminum nitride is an insulator. It's a very strong material. We use it in my lab as a refractory. It resists high temperature corrosion. Now, what's going on? The difference in electronegativity. These are covalent bonds, greater difference in electronegativity, higher bond energy. And that occurs in all of these columns as you go up. So an increase in electronegativity difference is an increase in bond strength, and an increase in bond strength means an increase in band gap energy. And some of these are really interesting. Indium antimonide has a band gap of about 0.2 of an electron volt, which means that its absorption edge is 7 times 10 to the minus 6, 7 micrometers, which puts it in the IR. And this is one of the materials that would be used as a sensor for night vision. Because what are you really sensing when you're looking at night? You're sensing heat. You don't see the human body. You see the heat coming from the human body. All right? So if everything's cold and there's no delta T, you don't see anything. Over here, cadmium sulfide. Cadmium sulfide is 5 times 10 to the minus 7. That's right smack dab in the middle of the visible. When I was a child, my father had a 35 millimeter camera. It had a cadmium sulfide light meter, and we would match the needle with the incoming radiation and cadmium sulfide. Well, I never understood why it was cadmium sulfide until I understood band gap, and obviously there it is. You can also think about what happens if you're photographing something that's dominantly red and your light meter is parked in the middle of the yellow. You wonder why your photographs are overexposed. Think about that sometime. Oh, so now, last thing I want to tell you is that that not only do you have solid semiconductors, you have liquid semiconductors. And when silicon melts, it's not a semiconductor. Silicon melts, the band gap collapses, and molten silicon behaves as a liquid metal. But for example, something like cadmium telluride, which is useful in night vision, cadmium telluride as a solid has a band gap on the order of 1.45 electron volts. As a liquid, it still has a band gap. It's about 0.3 electron volts. So it is parked down in the infrared. And the transition metal oxides also do this. Titania, liquid titania is dominantly an electronic conductor, not an ionic conductor, because its band gap is parked there. And this is of interest to some of the work in my lab where we're looking at trying to set the stage for lunar colonization, where we want to get oxygen out of the moon, the surface of the moon. The surface of the moon is not made of green cheese, I'm sorry to tell you. It's made dominantly of iron oxide and titanium oxide. That's why it's so brilliantly white. It's titania. So it's 50% oxygen but tightly bound. And if you want to electrolyze the moon, you have to somehow repress this liquid semiconduction. So that's a topic of research. So this is probably a good place to stay. And what we're going to do next day is we're going to start onto the treatment of solids and crystal. But I don't want a lot of moving. It's 11:47. We still have a few minutes. So let's see. What do we want to talk about? We'll move past this. We'll get to this next day. And what I wanted to talk about today was this image here. This image is an image of the first diode, rectifying solid-state diode. This was done at Bell Labs in Murray Hill, New Jersey in December of 1947. So what you're looking at here is a piece of single crystal germanium. Single crystal germanium and the various leads and so on. And this was able to perform the function of a diode. Now, if I told you that someday there would be 16 million of those on a piece of real estate about the size of your fingernail, you would say that I was crazy. All right? And so what's happened from that day to this day? Tom, do you think I could get the document camera on, please? So I'm going to show you where we've gone. This is let's see, I want to go to this. Oh, look at this. So let's look at Pentium. Here's Pentium. And then, okay. So we've got a gazillion of these things underneath the gold here. Everything's covered in gold because electrical engineers are very superstitious. They get nervous exposing wires, so they plate everything with gold because they heard somewhere that gold is chemically inert. So underneath there is, well, here you can see that there's the unit. So it's sitting there. So all of this, and here's the suspension, all of this spider web is being able to address all of the various devices. So it started with that first one. And here's the sort of the intermediate. This is taking the silicon that I showed you last day, and now Let's go as big, see? So these are individual devices that have been put on the silicon through photolithography. So what are we doing? What we're doing is we're making masks and we're conducting these doping operations to set up the various devices. And we can make many of them and then break them up and then eventually put them into something like this and so on. So that's the result of a long history of understanding the processing of devices based upon the chemistry that started with what? What started all of this? The search for octet stability. Never forget that. That's what started this, the search for octet stability. Okay, we'll see you on Friday.